All right, back from break. Here we've got another one of those practice sets of problems. So again, this was a previous year's midterm 3. And we're starting off with a lens problem. So lenses are pretty fundamental. And here is, this problem has actually 2 lenses in it. So we've got lens 1 and lens 2. And again, I'm starting off with a diagram. I mean, they tell us to actually part A on this problem, this first problem, is saying draw a diagram. So, and you know, you guys know that when you're working these problems, the diagrams at first just have some of the basic information in them. And then as you read through the problem, sometimes the diagrams have to be modified a bit. But I went ahead and drew the diagram out by getting that central reference line, placing my 2 lenses, lens 1 and lens 2, and then starting to identify distances. So the distance between the lenses was 40 centimeters. The original object is placed 30 centimeters to the left of a converging lens. So my first DO, the DO for lens 1, is 30 centimeters. Now notice, what I've got here is I've organized all of the information about lens 1 and lens 2. I don't want to get those mixed up. If I start writing this as DO lens 1, a lot of subscripts confuse me sometimes too, so I'm going to try and be really careful. So anything related to lens 1 is in this column, anything related to lens 2 is here. And then, so if I write DO, DI, F over here, it's got to be referring to lens 1. If I write DO, DI, F over here, it's got to be referring to lens 2. That's the convention I'm going to use in trying to solve this problem. So what else do they tell us? Oh, the second lens, this one has the mystery focal length that's unknown. So the first focal length is 20 centimeters. This one's unknown, but it's placed 40 centimeters from lens 1 to the right of the first lens. And then there's a final image, 50 centimeters. So let's see what we got. We got the DO for lens 1, that's 30. We've got the distance between the lenses, which for right now, we're just going to leave that as L. I'm going to call it L. And then DI, that's an I, is equal to 50 centimeters for lens 2. This is a real image because it's ending up on a screen. No, it's not ending up on a screen. It's a real image because it's on the side of the lens where the light actually is coming together. Okay, so it's let me restate that. It's on the side of the lens where the light actually is. So if we have a image showing up here, that would need to be a real image. So that's a positive 50, that's a positive 30. The 40, we're going to have to play around with that and see where the 40 comes into play. It's got to show up somewhere because the distance between the 2 lenses is going to make a difference on how this whole lensing system works. So let's start with lens 1. I got my diagram drawn and I'm actually feeling pretty good about it. Here is lens number 1. F is equal to 20, that was given. DO is equal to 30, that was given. So I can solve for DI. DI is equal to 60. So part B, solving for that, says that now the focal length was 20 and the object distance was 30. That's a real object creating a real image, just looking at lens 1. And it shows up right here. It shows up at 60. Now again, I got a ruler out. So I always, encourage students, get out that ruler and practice, play around with these rulers when you're solving these problems. So just seeing if I can track my ruler down. Here it is. Here's my ruler. And the ruler is clear. The ruler I'm using is clear. And what that allows me to do when I put it on my paper is I can still see everything through the ruler. And so I just come up with some kind of a scaling system. 1 centimeter equals this much distance, and then plot everything. So FDO, I got the DI. I wrote the DI in. Now this image from lens 1 is going to be the object for lens 2. Now this starts making me think of like that lab that we did with converging and diverging lenses. So what's going to happen here is that is going to be a virtual object for lens 2. The light is coming from here. It passes through here. The light's approaching lens 2. But the object of that for lens 2 is on the opposite side of the lens. So it's not on the side where the light's coming in. And that makes it a virtual object. So let's think about this. How far is this object for lens 2? How far is the object for lens 2 from lens 2? And that's going to be 60, this was 60 centimeters that we just solved, minus 40 is going to be 20 centimeters. So the object distance here is going to be 20 centimeters, but wait, it's a virtual object. I got to put a minus sign on it. So that's kind of all calculations that I have to do kind of conceptually. There's not one formula that's going to tell me exactly how to bring those numbers together. So I'm using my diagram and saying from here to here is 60 because that's the DO for lens 1. From here to here is 20 because I took 60 and subtracted off the 40. So the DO for lens 2 is going to be 40 minus 60. That's going to be minus 20 centimeters. Now I just needed to get a minus sign in here. Kind of is why I did this. I could have done it the other way and then added the minus sign by hand. That's fine. Anyway, the DO is negative 20. The DI we were given is positive 50. I can calculate the focal length now needed. The focal length needed is minus 33.3 centimeters. And that would make it a diverging lens. So what's happening here is lab. So it's kind of like the lab exercise that you guys remember, right? Because you did the lab. So this is why actually going through the labs is really important because you learn things there. So anyway, we've got a diverging lens and it's going to have a focal length of negative 33.3. Now in part C of the problem, it comes back and it starts talking about the final image. Is that going to be real or virtual? What's its height going to be? Well, it's going to be real, right? The final image, final image is here. So the final image is here, and that's going to be real. And I didn't get that added in my diagram, did I? So I did such a nice job here of measuring everything out and getting the image, but now I need to take this line and continue it over to here. So I'm taking the line from the center of lens 2 through the object, and that's going to give me an image right here. You guys can see that image? I could go back and draw it in, but it's going to cover up some of the calculations. Anyway, the image, it's from here. The image is going to be from here down. So it's going to be this big. It's going to be that big. So let's see what we get. So lens 1, the starting height of the object was 1.1 centimeters. The magnification here that we got was minus 2. That says that this image is going to be at minus 2.20 centimeters. Moving on to lens 2, this now is the object. So I now have an object height. I'm going to go ahead and keep using the minus 2.20. The magnification here is going to be 2.5 based on my DI and my DO measurements, but it's going to be positive. There is not, the diverging lens is not going to create an inversion the way that the converging lens did. And so HI is equal to M times HO, putting those numbers in. This is going to be a real image, and it's going to be not inverted relative to its object. It's going to continue to be in downwards facing, and 5.50 centimeters is the size. So it's going to be larger than its object by a factor of 2.50. Okay, so good problem. Practice doing some drawings with these. Practice doing some drawings for the lens examples. That's a good skill to have in place for these particular problems that we're looking at on the midterm. Okay, let's move on and take a look at problem 2. Problem 2 is saying this. It's saying that we're going to use a telescope, and we're going to be looking at Mars, and we're going to be trying to pick out features on the surface. Now, it's not an especially large telescope. It's like 40 centimeters in diameter. The telescope that we have here at Laney College, the Laney telescope, has a diameter of about 25 centimeters, and it's, you know, we were able to get that out and get a really good look. A lot of fun looking at features on the surface of the moon, looking at the rings of Saturn, looking at moons of Saturn and Jupiter, looking at Venus, illumination from the sun. Venus actually goes through different phases depending on where it is in its orbit relative to the Earth. Anyway, so we've got a telescope with a diameter of 40 centimeters, and we're going to be looking at Mars, and we want to get an idea of how much detail could we see in the features. Now, in chapter 35, we looked at, let me jump ahead here. Let's look at solutions. There we go, that looks better. So here we are on the surface of Mars with two objects separated by some distance. And what's going to happen is light from those two locations on the surface of Mars are going to come through my telescope. Now it says that the first thing they run into is not a lens, but it's a collecting mirror. And that mirror has a diameter of 40 centimeters. We're going to use that to determine what is the diffraction resolution limit. So this is what we've talked about in class. Is that with optical devices, there's kind of a trade-off. What happens is, if we use a mirror or a lens to collect and gather a bunch of light and focus it, if we make the lens in the mirror bigger and bigger, we help eliminate the uncertainties due to diffraction. So what's happening here is that we're getting the light that comes through doesn't land at just one location. It's spread out due to the diffraction effect. If we open up the aperture, if we allow a wider sample of light to come in, then the diffraction effects go down. But the opposite effect, or the effect that we don't want from that, is if I make the mirror and the lens bigger and bigger and bigger in terms of diameter in order to eliminate diffraction, I have to make sure that that lens or that mirror is built to very exacting specifications. The curvature on that lens or the curvature on that mirror needs to be built very, very carefully, and that becomes its own engineering difficulty. So again, it's kind of this trade-off between, do I make the mirror and lens bigger? If I do that, there's a possibility I'll lose resolution because of the imperfections in the mirror or the lens. Okay. Anyway, at 40 centimeters, the effect due to diffraction, this is just a diffraction limit, we showed was given by the formula of theta is 1.22 wavelength divided by the diameter. Now, we want the theta to be as small as possible. So smaller and smaller angles are telling us we can see better and better resolution. This is an angle of resolution. And so to get better and better resolution, we want to use shorter wavelength light, maybe something in the blue end of the spectrum, and we want to make the diameter as large as possible. Well, in this example, it's at 40 centimeters, and the wavelength that they give us in the problem, they say that this telescope, we can use a blue filter, which only allows the blue light to come through, and that's going to help give us better resolution. So the theta that we calculate from this, now to get theta, I have to make sure in the formula the wavelength and the diameter are using the same units. The units have got to cancel out so that the answer is unitless. And as we've said from Physics 3A through Physics 3B, if I'm calculating an angle and the units just all drop out, that means I'm in radians. Radians are the unitless unit. So that's kind of a natural unit that things come out in. So when I carried out this formula, it's coming out in radians, 1.3, 10 to the minus 6 radians. That converts over into 7.5, 10 to the minus 5 degrees. That's a pretty small angle. So the angular resolution is given by these numbers. And then if I move over to something in the red end of the spectrum, so maybe I use a red filter to try and bring out certain features. But what I have to be aware of is if I go to longer wavelength, the angular resolution won't be as good. I will not be able to distinguish objects that are really close to each other. So using the formula for angular resolution, plugging all the numbers in, making sure that the units are canceling out by putting in that 10 to the 7, I ended up with 2.07, 10 to the minus 6 radians. That's bigger than it used to be. And that means that I won't be able to see things in as much detail. Here is the conversion over into degrees. Now in part B of the problem it says, let's specifically ask if Mars is 88.6 million kilometers away, that's closest approach, right? Yeah, so at Mars' closest approach, it's kind of directly, well not directly overhead, but as directly overhead as it gets, at maybe midnight or something, what we can do is come up to this diagram and say, now that we've calculated the angle that represents the limit of resolution for diffraction, and then if I multiply that by L, I'm going to get D. So D is equal to L times theta. Now for this formula too, theta's got to be in radians. So whenever we have a formula where theta is just sitting out there by itself as a factor, it's not the sine of theta, it's not the cosine of theta, that theta is going to be in radians. So I'm putting in the distance in kilometers and then putting in the value for the blue light in radians, multiplying those, and what I'm coming up with is 116 kilometers. So it's a fairly modest telescope. And it says that with this telescope, everything else in the telescope's been built perfectly. The limits due to diffraction would still mean that for objects closer than about 116 kilometers, I'm not going to be able to pick those out. Okay, so if there are two different features in the geography along that range, and they are closer than 116 kilometers, I won't be able to discern that amount of detail. It will just look fuzzy at that level if I try and look that closely. Now if I move on to the red light, the resolution is going to be not even that good. So here, the angle using the red light, and again, maybe there's a trade-off here. Maybe there's something in the red filter that I'm going to pick up that I'm not seeing in the blue filter. But as far as diffraction is concerned, the diffraction effects are going to become larger with the larger wavelengths. And so now it's at 183 kilometers. So I'm not going to be able to do detailed, really highly detailed mapping of the surface of Mars using this telescope. On the other hand, we're going to be able to see some pretty good features, right? If I can really start to pick up things down to the level of a few hundred kilometers, very general trends across the surface, those kind of things we're going to be able to pick up. Questions on that? So again, on these chapters on light and optics and interference effects, we've got two-slit interference, we've got diffraction gratings, we have diffraction, we have limits of resolution, we have thin film interference, and we have polarization is the one I was trying to remember. So polarization is in there too. We also have single refractive surfaces. So, you know, the few examples that we've looked at here, these are good examples to go through in terms of looking at lenses and some of the interference effects. Make sure you're going back and looking at more of the homework problems and reviewing the examples from class. Questions come up, stop by. Questions are always welcome. Do not hesitate to stop by with questions. Let's move on. So in problem 3, what we're doing is we've introduced these new formulas in terms of calculating particles' momentum, particles' kinetic energy, and we've introduced something called the total energy, and that's something we didn't even talk about in classical physics. But relativity introduces this idea of total energy, and it's the total energy that actually is getting conserved in reactions. Velocity is fairly familiar, but relativity gives us new formulas for determining velocity and then frequencies and wavelengths. So this problem is just really kind of a review of all the different formulas that we've, kind of the basic general formulas that we've developed. And it used to be that I would guarantee students that a problem like this is going to show up on the exam. I'm not going to go so far as to guarantee that it's going to be there, but this is certainly something you should practice. Because the reason I started adding problems like this to the midterms is that students would say, wow, there's just so many formulas I can't keep track of them. And I'm sympathetic to that. And so what I wanted to do is come up with something that would help reinforce what are the formulas that are completely general? What are the formulas that will work all the time? And so this problem is kind of a list of those. In this particular problem, it says that, let's read and see what we've got. We have 3 different types of particles. We have a photon, which has no mass. We have an electron with a mass of 511 keV. These are masses. I hope they look familiar. And then a proton, which has a mass of 938 million eV. So with these 3 particles, it says what would it take so that they would each have a wavelength of 2 picometers? How much energy, for example, would a photon need to have a wavelength of 2 picometers? How much energy would an electron need? How much energy would a proton need, such that all 3 of these would have the very same wavelength? So in this particular example, let's start out and say, hey, everybody, we want everybody to end up with a wavelength of 2 picometers. And then I'm going to write down one of our standard formulas from quantum physics. So quantum physics and kind of relativity combined say that PC is equal to hc over the wavelength. That always works. It works with particles with no mass. That works with particles with mass. So that's a very useful formula. Now, I can write in values for hc as 1240. Now, I'm going to work in terms of keV. And the reason for that is the wavelength was given in picometers. So if I work with distances in picometers, then for the 1240, for hc, I can use 1240 keV times picometers. Those are going to be handy sets of units, and the picometers will cancel out. So I'll be left with keV. So let's see how far we can get just by saying that. Now, since PC is equal to hc over wavelength, that is a completely general formula that always works. I can use that and calculate the momentum for each of these particles. Now it seems a little funny, but when we're down at the level of particles, photons, electrons, protons, when we talk about the masses of these particles, we often are working in terms of mc squared. So it's not really their mass, it's their mass energy, but we just call it mass. So the mass of the photon is now written in keV, 0 keV. The electron 511 keV. The proton, you could write this as 938 MeV, or you could write it as 938,000. Now that would start to create some problems maybe with significant figures, so I'm going to hold off on that and just stick with the 3 sig figs. On the next line, what I chose to write down first was the momentum. Is that what they asked for? They actually did. They asked for momentum first. Now, I don't have to follow the ordering that they've given me. I could answer these in any order I want. But I'm going to go ahead and answer PC because if all of them have the same wavelength, they all have the same momentum. So the momentum here is going to be 620 keV, 620 keV, 620 keV. So that line, I can just write those in immediately. I don't have to do 3 calculations. I can just do 1 because I'm going to end up with the same value for each of those. Now, from relativity, so this formula was from quantum physics, from relativity, I know that E squared is equal to MC squared plus PC squared, and I've already listed the values of MC squared, and then I've also written down PC from just 1 calculation. Everybody's got the same PC. I can plug these numbers in, take a square root, solve for total energy. So the total energy for the photon, well, for the photon, m is equal to 0, so the total energy is going to be 620 keV. That number did not change. But for the electron does have mass, and that means that the total energy is some combination of the mass and the momentum. Now, it's not just adding the mass and momentum, it's kind of like Pythagorean's theorem. I have to square the mass, square the momentum, add them together, and take a square root. And for the electron, that gives me 803 keV. So that's a significant amount of momentum for an electron. What about the proton? Well, the proton is going to turn out to be the difficult particle. We're going to have to be a little more careful working with this. What I did is I took the 938,000 keV from here. I used the very same formula. And then I combined this in. But when I carried out the calculation, what I got was 938,000.205 keV. Now that's got me just a little bit worried because I'm trying to keep 9 significant figures. Is that reliable? And sometimes it is and sometimes it's not. It turns out that depending on what the formulas look like, sometimes this approach actually works. Now, the mass of the proton is not exactly 938,000, but this extra piece that's added on could likely be reliable. So I'm going to write this down. I put it in parentheses just to point out that it's making me a little nervous right now, but it might work. Let's see what happens when we calculate kinetic energy. So I'm going to move on. I may want to come back and revisit that. But the electron looks fine, the photon looks fine. For kinetic energies, we can take E minus mc squared. Now, these formulas are all coming from relativity now. The total energy formula, and the kinetic energy formula, and the velocity, these 3 formulas are coming from relativity. And it guarantees that the total energy minus mc squared will tell me how much of the energy is kinetic. And what we find with this is that the total energy, which is 620 keV, the photons don't have any mass, so this works out to be 620. So notice for the photon, photon has no mass, and that means that its momentum, its total energy, and its kinetic energy will all be the same value. Now what I've done is I've gone through and just calculated those as separate steps, and that's fine. What this is allowing me to do by writing down all of the very reliable formulas, I'm kind of getting myself into a pattern of just plugging those numbers into the calculator, write the formula down, plug it in, making sure that we have the right formulas in place. So this is general, this is general, this is general. These three will work. Now when I plug in for the kinetic energy of the electron, that works out to be 292 keV. Again, everything's looking fine here. When I plug in for the proton and subtract off the mass, I'm left with just 205 eV. So again, I'm going to come back and double check. This is making me really nervous, as it should, but I'm going to come back and double check here in just a minute. But I want to finish this out. From relativity, here's a formula. I think we used this in a few examples. One of the formulas from relativity tells us if I take the momentum, divide by the total energy, multiply it by c, that'll tell me how fast I'm going. So I could have calculated gamma, but this formula actually is a quicker way to go in and calculate the velocity. So I can take pc divided by energy. Now for the photon, that ratio is 1.00. So the photon is traveling, surprisingly enough, at 1.00 times c. The photons are traveling at the speed of photons. Electrons, I can get their speed by taking momentum, dividing by the total energy. Turns out that these electrons, with a wavelength of 2 picometers, would be traveling at 77.2% of c. And then if this is a reliable number, the 205 eV, that can be divided through by the 938 MeV, and that worked out to be 0.000661 times c. I know it seems like that's hardly moving, but put that into meters per second and you'll find out it's going pretty fast. So that proton is actually moving at a really good speed. And then the last thing they asked for was frequency. Now to calculate frequency, let's see. This is a general formula from quantum physics. It says that the frequency of a particle depends on how much total energy it has divided by Planck's constant. So this is a general formula that applies to everybody. Just like P equals h over lambda, that was the other one. So relativity, 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 quantum physics, quantum physics. And I've written these in the forms that work all the time. Now there are variations on these that have been adapted for, say, photons exclusively. Those won't work for electrons and protons. Electrons and protons have mass. So I got to stick with these formulas. So if I'm calculating a frequency, do not go back and try and relate this to the wavelength. It won't work. And that's because the wave speed is not something we've really determined in quantum physics. So don't get the frequency from the wavelength. Get the frequency from the total energy using this formula. Now when I did that with the photon, the total energy was in keV. Now I didn't write it down here. I should have. I just go back in my notes, my one page of notes that I take into the exam. I'm going to write down Planck's constant in eV seconds, which is like 4.14 10 to the minus 15. So I'm going to have H and H bar in my notes, and which is a good idea. And I'm going to have them written in terms of units of joule seconds, but I'm also going to have them written in terms of eV seconds, because that's going to be really handy. So doing that, I ended up with 1.5, 10 to the 20th. Make sure you check units on these. Make sure that the EVs are canceling out. For the electron, it's got a little more total energy. It's got a little higher frequency. The proton has a lot more total energy, and that's because its mass is so large. So this is bigger by more than a factor of 1,000 in terms of its frequency. All right, let's check and see. The electron's total energy was 800 keV. The proton's total energy is 900 MeV. So again, more than a factor of 1,000. Now this is the stuff that I said we were going to come back and check. What we can do is we can take a classical approach. What happens, as you can see with the formulas from relativity, is when we start adding these things together, we could run into problems with significant figures. What's happening here is that the proton's not going super, super fast. And as a result, its momentum is tiny compared with its mass, and then we run into these issues with significant figures. So what we can do is go back and use the formula from classical physics. Formula from classical physics for kinetic energy would be 1/2 mv squared. Now 1/2 mv squared can be written as p squared over 2m. By adding some factors of c, I can calculate the kinetic energy of an object by taking its momentum squared divided by 2 times its mass. Now, this formula only works at low speeds because it's based on 1/2 mv squared is where it's coming from. So I'm going to plug numbers back in. I got 3 sig figs on the momentum. I plug that in and square it. I have 3 sig figs on the mass. 938,000 keV. I want the keVs to cancel here. And what that gave me was 0.205 keV or 205 eV. It works. So I used the low velocity classical formula and showed that this is one of those instances where the formulas from relativity work, even though this makes me a little nervous. And there are reasons behind that mathematically that stop by office hours and we can talk more about why this works. But in any case, this number looks good, so that reinforces what we've done here. The very last thing they ask in part, there's a part B, I guess, and it says that if we were using some kind of a voltage to speed up the electron and the proton, what would the voltages need to be? And the voltage numbers need to match the kinetic energy numbers. So if I want to bring an electron up to 292 keV, I can just factor out the charge, which is E. So the E's cancel here, and I end up with 292,000 volts. That's what I would need for the electron. But look, for the proton, I only need 205 volts. So the electron's going to need more than 1,000 times the voltage to get up to the same momentum and the same wavelength compared with the proton. Okay. So that's what it looks like. That's what the calculations look like once you start using quantum mechanics and once we start using relativity in these problems. So any questions on this, stop by. Let's take a look at that last problem. We'll wrap things up here. The last problem is saying that there's an electron in a molecule, and it's being confined to a region of 240 picometers. So what this example is, it's looking at, for an electron confined to a certain region, what would be the electron quantum states? Now this is what in the textbook we call the infinite potential well. So it's a particle that's able to move around within a certain region, but there are firm boundaries as to where it's moving. Now for the electron, where the boundaries are coming from, is that there are nuclei that are positively charged and they're holding the electrons in place. So you've got these nuclei holding the electrons in place, and we're going to model that as if there's some kind of a firm boundary. Now what we're also doing here is we're only doing a one-dimensional example. So 3 dimensions is more complicated. This is only asking for 1 dimension. And so it's not the best representation of what actually happens inside an atom or molecule, but it's a pretty reasonable first effort at going in and using some actual quantum mechanics, stuff we learned in chapter 38, to estimate how much energy these electrons would have. So using the formula that we derived for the one-dimensional infinite potential well, these are kinetic energies. Now I know in the textbook they're using big E, and I think in lecture I probably used big E too, but I just want to remind people that remind you guys, that we're only using, what we're calculating here is only the kinetic energies of the electrons. Now this is the formula we've derived. So for the HC factor I can put in 1240 eV nanometers squared. It's an electron, so for MC squared I'm going to put in 511,000 eV. Now the L is 240 nanometers. Oh, I need to close off that 0. 0.240, that's a 0. And what this formula is telling me is that I can calculate the kinetic energies of all the possible quantum states by taking n squared times all of this calculation, and all of that calculation gave 6.53 eV. So I can take multiples of that, 6.53, and what it says is for state numbers 1, 2, 3, and 4 that look like this. These are the wave functions. So these are the wave functions, what they look like, and it asked to draw those, right? So I did. Let's see. Find the wavelength for each of the possible electron states. Let me go back and I'm going to read through the problem and see how much we've answered and how much is left. What's the wavelength for each of the possible electron states? So I can draw these states, and remember, these are sine functions, so they need to look like sine functions, and they need to zero out at the ends. So here is quantum state 1, 2, 3, 4, the wave functions. The wavelengths for these are going to be given by 2L over n. You can go back and check. That's only half of a wave. The full wavelength would be twice as much, so that would be 480 picometers. Now in state number 2, that is a full wavelength. So if I think of that as 2L, it needs to get divided by n. And then the pattern continues. So 480 picometers to 40, 160, and 120 as I divide through by 1, 2, 3, and 4. Okay, so for the sine functions, with a particle confined to a certain region, I can use that 2L divided by n to determine the wavelengths for each of those. B says find the kinetic energies, and for that we're going to use the kinetic energy formula. And so I've plugged into the formula. So that wave function, that one, that one, that one, represent quantum states with this much kinetic energy. So I can't have an electron at rest. I cannot have an electron that at rest is kind of a classical way to state this, but I can't have an electron with no kinetic energy. An electron confined within some region will always have some minimum amount of kinetic energy to it, and for this particular example, the 240 picometer size tells us the kinetic energy will be at least 6.53 eV. That's the lowest energy quantum state available to the electron. Okay, and then the others just get bigger, and they get bigger quite fast because there's just an n squared right here. Okay, and that was part B. And then C, C is back up here. Draw diagrams, there we go. So diagrams for the wave functions, I already drew those back when they were asking about the wavelengths. So I drew the pictures so I could see and double check the wavelength calculations I was using. And then in D, now D is asking to draw the probability distributions, and the probability distributions are going to be sine squared. I have to take the wave functions and square them, and so the probability distributions, sine squared functions look different from sine functions. So don't get these mixed up. In fact, make sure you're clear on what the sine function looks like. That's the wave function itself. This is the wave function squared. Wave function squareds give probability densities. So it's in state number 1, it's more likely that the electron is in the central region. In state 2, there are 2 regions of reasonably high probability, but there's a depletion of probability right in the middle. Right in the middle, where you might expect the probability would be really high, it's not. And that's a quantum mechanics effect. And that's what we've seen in the chapter, is using the Schrodinger equation. Using the Schrodinger equation, we've gone in and determined what the properties of the wave functions are going to be. And then wave function 3, wave function 4, there's going to be 3 distinct regions of probability, and here there's going to be 4. And then finally in part E, this problem went on and on. So in part E, we're calculating the energy and the wavelengths of photons created in all the possible transitions. That's too many transitions. That's an unreasonable amount of work to do. Okay, here they are. So if I'm thinking this is just kinetic energies, then this is my 0 for kinetic energy. The first quantum state shows up here at 6.53, 26.1, there's a third quantum state at 58.8, there's a fourth quantum state at 104.5. How many different ways could transitions occur? Well, I could go from 4 to 1, 3 to 1, 2 to 1. I go from 4 to 2, 3 to 2, and then I could do from 4 to 3. Which are going to be the big energy transitions. Well, in this case, it looks like the gap between 4 and 3 is the really big one. So 4 to 1, 4 to 2, 4 to 3, I'm thinking those are going to be the big ones. Let's see what happens here. 2 to 1, I can get that by taking 26.1 eV, subtracting 6.5. That worked out to be 19.6. 3 to 1 is a difference of energy of 52.3. That's the energy of the photon. So the photon energies are going to be the difference in energy between the 2 quantum states. So if the electron drops from 4 to 1, that's going to be 98 eV. That's a lot. From 3 to 2 is 32.7, 4 to 2 is 78.4. So yeah, the electrons dropping from quantum state 4 are the ones with the most energy, right? They're dropping from that really high quantum state. And then what we can do is we can take the wavelengths, or we can calculate the wavelengths by taking hc and dividing through by E. Now the hc here is going to be our old friend, 1240 eV nanometers, and that's going to work, right, to come up with all the wavelengths. So we're getting really short wavelengths for these drops from state 4. All right, I think we're getting close to what we need to take a break here, or wait a minute, I think we're wrapping things up for the day here. I don't think it's time to take another break, right? So yeah, we're done. Sorry about that. I hope I didn't frighten anybody that we had more to look at. But we've got these problems from optics, from looking at light, and we've got these problems from relativity and quantum physics. So take a look at these. Whatever questions you guys have, stop by, and we will get those looked at.